not a huge difference between electric potential and electric potential difference. It's very simply the difference in the electric potential between 2 points. So we know previously that from the last video or from class that at this specific location right here, I have a certain amount of electric potential. I don't have actual energy at this point, but the electric potential will tell me how much potential energy I will get at this point for a given amount of charge at that location. So as an example, we'll say this is 10 volts. So 10 volts here means that for every coulomb of charge I put here, I will get 10 joules of usable energy, because remember, another way of saying volt is joule per coulomb. 10 joules per coulomb of charge I put at this point. Well, if I had another point here, let's say that this is 5 volts, right? Well, this has an electric potential of 5 volts. This has an electric potential of 10. The electric potential difference is quite simply the difference between these points. So whereas electric potential is the potential at each of those points, the difference here will be your change in voltage. So the change in voltage between these points, 10 minus 5 in this case, my change in voltage would be 5 volts. Now it's important to realize this is the mathematical definition of voltage. It's the amount of potential energy divided by the charge in question. Right? You're dividing out the charge so that you very simply just get a location. It's independent of charge. This is your mathematical definition, which will apply to both a uniform and a non-uniform field, because it is just the definition of what voltage is, what electric potential difference is. To take a look at this now and how we derive these equations in class, well, we know that from up here, we know that the voltage equals your change in potential energy divided by charge. We also know that for a uniform electric field, that our change in potential energy also equals the charge times the electric field times D. It equals QED. So if I replace this with what we know to be the change in potential energy for a uniform field, and we divide that by charge, well, the charge cancels out here, and all we're left with is ED. So what we have here is that our change in voltage is equal to the electric field strength, the uniform electric field strength, times the distance we move this charge. So to show an example here, if I were to take, let's say, a 2,000 Newton per Coulomb electric field, and I will quickly draw one here. I'll put my positive plate. I will put my negative plate. If I were to draw my field lines, we should know that they go from positive to negative by now. So if I assign this a value, this is 2,000 newtons per coulomb. That's how strong that electric field is. And let's say I want to know what the potential difference is between this point and this point here. And we will say that that is a distance of half a meter, 0.5 meters. So I have 0.5 meters. That's the difference in height between these 2 points, or the distance, and I have my electric field strength here. Since this is a uniform field, all I need to do is take a look and say the change in voltage, the potential difference, is going to be my electric field strength times the distance the difference in distance between these two locations. So I know my change in voltage in this case will be 2,000, which is my electric field strength, multiplied by the 0.5 meters, which hopefully you don't need a calculator to see that this is 1,000 volts. So for this uniform field, if I go anywhere within this field and I look at 2 points that are half a meter away from one another, half a meter above or below one another, I'm going to always have the same change in voltage, 1,000 volts. That does not mean that this point is 1,000 volts, this is 0. It simply means that whatever these voltages are, the specific difference between them is going to be 1,000 every time we check, so long as the distance between the 2 points we're looking at is 0.5 meters. That will obviously change if we start to change our distance. If we want to look at a point charge, we use the same mathematical definition, but we're going to derive a slightly different equation. So we know that from previously, our change in voltage is our change in potential energy divided by our charge. We're getting rid of that charge, which is why we wind up with 10 volts per coulomb. I'm sorry, 10 volts, which is 10 joules per coulomb. Joules per coulomb. Energy per charge. That's where that comes from. We know this is a little bit different. We know that the change in potential energy for a point charge is equal to K QQ over D. So K times one charge times the other charge divided by distance. We derived that in class. I should be able to take that, plug it down into this equation. So if I replace my change in potential energy with K times my charges divided by my distance, that is this. Well, I need to take into account the fact that I'm dividing by Q, which I believe the easiest way to see that is just multiply by 1 over Q. If we do that, you hopefully see that our Q's are going to cancel out, and what I'm going to wind up with is K Q over D. So our change in voltage for a non-uniform field for a point charge will be Coulomb's constant times our point charge divided by the distance from that point charge. So if I were to use, let's say the example we have previously, if we look up here, I will have a point that is, let's say about 0.6 meters away from our charge. Now remember, this is just a location. There's no charge here. This is a charge. For this example, let's assign that a charge of 5 microcoulombs. So we'll say that 5 microcoulombs, 5 times 10 to the negative 6 coulombs. So that's the charge of my actual point charge. So now if we take a look and I want to know what's the change in voltage from this point to this point. Well, what I'm going to do is I'm going to plug in my change in voltage is going to equal Coulomb's constant, 8.99 times 10 to the 9th. My charge, which in this case is 5 microcoulombs, 5 times 10 to the negative 6. I'm going to divide that by the distance between my 2 points, how far I've moved away from this point charge, which is 0.6 meters. So if I divide by 0.6 meters, this I unfortunately cannot do in my head, so we will have to plug this into the calculator. So we have 8.99 times 10 to the 9th Coulomb's constant. I will multiply that by 5 times 10 to the negative 6th. I'll then divide that by 0.6. And I wind up with a very large change in voltage, 74,900, and I'll round that to 17 volts. Now that is a high amount of voltage here, but we actually have a fairly large charge when we're talking about only 0.6 meters. So as stated previously, your main definition here, this is your mathematical definition. What you want to take into account with a uniform field is the field strength and the distance you've moved between 2 points within that field. And if you'd like to know the voltage, your potential difference between a point, a certain distance from a charge, you have to calculate using Coulomb's constant the value of the point charge itself, as well as the distance that you are from that point charge.